Okay, here we are, and so we can start with the correction. So thanks, Pratyush.
Thanks again for being here.
Right. So I will share my screen and let's see. Do people have any questions about the material last time? Don't be shy. Okay, so let's use it as an opportunity. So we will be efficient today. Let's use it as an opportunity to remind you of what the whole idea is. So the whole idea is to take a high-dimensional system and try to come up with a model we can make good predictions about the future of the system. And there are two ways. So this idea, which looks like a variational autoencoder, is being used by many different groups in order to come up with a reaction coordinate that can then be biased in metadynamics, or that can be used to analyze a simulation and see what has been going on. But this is where a lot of nuances come into the picture as to how exactly do you define this. First question is, when you have, and so this input, and this is the only question that was asked on Slack, which is this input, what should this input be? So when you're trying to come up with a reaction coordinate for a molecular system, this input is generally some symmetry invariant order parameters. This could be, for example, all dihedrals in a protein, or all contact maps in the protein ligand system, and something like that. And the output that you're trying to predict could be, for example, the same inputs that you put in, but their value slightly into the future. And this delta T is a tuning parameter. It could be as small as picoseconds. It could be as large as even nanoseconds. And so this is one place where the variation comes in. If you're doing traditional variational autoencoder, this output will be the same as the input. You're just trying to come up with a model which can recapture what you fed into the model, and there won't be delta T. Delta T is equal to be 0. So in this information bottleneck approach, we set delta T equal to positive, and the output is generally not the same as the input. The output is the state of the system. And that's the first. So two key variations so far. We are predicting into the future, and we are not predicting all coordinates. We are trying to predict the value of some state. Which state is this system going to be in? And then this bottleneck variable that you have here, when you do variational autoencoder, you typically assume a Gaussian prior. So you assume that the probability density of this is just one Gaussian. In our case, we assume this is a mixture of Gaussians, and this is what allows us to learn the number of states in this system. So when you start using the code, all of this might sound complicated, but it's crucial to understanding. However, while using the code, the way it is done, it's quite, you don't have to go and tune too many things yourself. It's very easy to use things just by specifying some parameters like you would do in a plumed input file. And again, to recap, and we will go to the tutorial and we will see this for alanine dipeptide, you can start with your initial definition of states along any order parameter, or you could just do a temporal definition where you say time is equal to 0 to 1 nanosecond is state 1, time is equal to 1 nanosecond to 2 nanosecond is state 2, something like that. So you define it along some order parameter. If you had protein ligand dissociation, the best way to define initial states would be to just do it along the distance between the protein center of binding pocket center of mass and the ligand center of mass. This is the type of variable that people traditionally used to bias metadynamics, right? Just some protein ligand distance. So instead of biasing it, you take it to define your initial states. And as this SPIB method, state predictive information bottleneck, we call it SPIB, as it progresses, depending on how far into the future you're trying to predict, the populations of the state disappear. If you're predicting very far into the future, which is already 2 picosecond, you get only 2 states. If you're predicting half a picosecond into the future, you get 3 states. And so this is something we are still trying to think about, if there is a obvious choice of what delta T to take in order to come up with a reaction coordinate for biasing. But as you can imagine, there is no real one answer to this. If you're trying to speed up the movement between, if you're worried about the movement between these two basins, then you should start with half a picosecond. But then this is already fast, so it does not really matter. So the best way to use this is to go with a conservative slow delta T and then just start biasing it and see what's going on. And there is theoretical reason to believe as to why this thing with a certain time lag is indeed the committer for the system, which is known to be the true reaction contact. So any questions about this before we go to the tutorials?
Yeah, one question, just to
Please.
make sure, when you have like in figure B, those are the argmax of your outputs, right? Like
Correct,
you might
correct.
have, yep.
Yeah, so because the probabilities, some of the states will have, as you see in the tutorial, some of the states will still have very, very small probabilities, like close to 0. Good question. Any more questions? Okay, great. So this is quite true in general in machine learning. People, the models give you probabilities for something, and if you want to really clear, and these probabilities are changed to a deterministic assignment by using Rmax. So that's quite common. Okay, I didn't want to show you this. Let's go to, yeah, here we are. So this one I already ran last time. Let's open it in Colab. Let me close this one. Yeah, leave it. Okay. Any questions about this first tutorial? Was anything not clear in this one? Were people able to run it? Let me flip my way of answering asking questions. If you were able to run it, can you type yes in the chat? Great. That's good to know. So it looks like everyone was able to run. And so here, let's look at the syntax above, which is going to be useful for all possible problems. So any questions about the parameters that we have over here? Did anyone have any questions about these? Okay, so that was all easy because it was already done. Now the main thing, is there anyone who was able to try these exercises? I would appreciate it if you just type yes or no. Otherwise, it's a bit of cognitive dissonance. If it feels like I'm talking into the void. Okay, that's fine. Was there anyone who was able to try it? So this requires a bit of Python. Aside from 3B, yes, that's great, Pavel. Pavel, would you like to unmute yourself and talk with me a little bit? If you don't want to, that's okay.
Yeah, sure, no problem.
Great, I appreciate it. Okay, Pavel, so apart from 3B, okay, yes. Let's start with 1. And I'm going, so in 1, keeping everything else, change the parameter dt so that the number of convert states is 1, 2, more than 4. So in order to get one convert state, I'm going to tell the answer to all of these. And Pavel, since you tried it, I would really appreciate it if you tell me that you got the same answer, or if you got some other answer, and then we can have a discussion. Does that sound fair?
Yeah, sure.
Great. So in order to get the number of convert states is equal to 1, which means that you are saying all barriers, all low-lying barriers do not matter. Only one barrier, basically all barriers should disappear, right? If you had to, let me actually open this also. So if you look at my, can you see my PowerPoint?
Yes.
Okay, so as you can see in alanine dipeptide, in general, as you increase the delta T, the number of convert states starts to go down. So as you go to delta T is equal to infinity, the number of convert states should go to 1. And at some point, it should just become irrelevant. So basically, the answer to A is a large enough delta T. I think in this case, if you took a delta T of 1 nanosecond, you're almost certainly, or 10 nanosecond, you're almost certainly going to get 1.
I don't remember what are the units,
Yeah,
or I don't know.
Yeah, there is no unit here. You're right. There is no unit here. So There is no unit here. You're right. And as you start decreasing the value of delta t, at some point you will get 2 states, at some point you will get 3 states, and eventually it will become more than 4 states. Does that sound good?
Yeah.
Okay. And and you can plot this, and the plot this plot is given in the paper. So let's just look at that plot together.
Oh, I actually didn't plot it, but yes, I have the table.
Hopefully you have the intuition for it. Yeah. So if you look at this, in general, you don't have to plot it, but as you work on for debugging, if you start working on a complicated system, I recommend this is the first test you should do. So it's over here. So as you can see, as the delta t value is very large, so what are we plotting here? We are plotting the population of different states as a function of delta t. So as delta t value is small, you get many states show that they have. So as you can see, 6 out of the 10 states disappear. Their population becomes 0 very quickly. This is the bottom line. However, for delta t between 0.1 unit to 1 unit, 4 of the states tend to have a finite converged population. As delta t gets close to 1 and further, you recover 3 states. As delta t becomes even larger, you recover 2 states. And if you pushed it beyond here, these 2 states will disappear and you will always be left with 1 state. So that's the answer over there. In 3A, did it work, Pavel?
So the training was running for forever, and it was late in the
Yeah.
evening, so I just closed it. So I assume
Yeah.
it's not supposed to work.
It won't work. You will get garbage.
That's
If
right.
you, however, did x is equal to y, and maybe this will require a bit of coding, and you will have to go and generate grids which are rotated. But basically, the point here is that if you do it along x is equal to y, which is not the perfect reaction coordinate, or if you do it along, let's go to the potential over here. If you this is done initial states along x. The exercise suggested do it along y. So the initial states are divided like this. That's completely wrong. You're completely missing out on this low degree of freedom. So in this case, you will find that if you rotate the initial state assignment at 45 degrees, 60 degree, 80 degree, it will still work. It's only when you completely orthogonalize it, it's not going to work. If you think about that in the context of alanine dipeptide, it means that if you do it along phi, it's going to work. Turns out, if you do it along psi, it still works. So I can show you. And this is something maybe, and this is useful because we know that for alanine dipeptide, psi is actually quite a bad collective variable. If you try to do metadynamics along psi, it will show hysteresis. You will get free energy, but the sampling will not improve. So I think I have that plot over here. There you go. The discretization of psi. This is what I meant, right? This is equivalent to doing it along y. You can see it still works quite beautifully. You still get 3 states converged. And I think this is one of those papers which we had the hardest time getting it published in State Predictive Information in JCP, but the ideas are actually possibly more robust than any paper I have written. So here you can see that along psi, you still get exactly the same 3-state population as you would have gotten if you had discretized along phi. Now you can push it even further and try to discretize it along theta, which is a completely random dihedral, which theta does not do a good job of distinguishing any of the bases. If you do it along theta, then it does not work. Then you will have the same experience which Pavel had in the model system by doing it along y. The code will keep working or it will stop and not give you the right answer. So what is the lesson that we learned from here? The lesson is that in order to discretize, we know that phi is close to the reaction coordinate. We know that psi is really far from the reaction coordinate. Yet psi will also work. You don't have to be very close to the reaction coordinate. The method iterates and give you the good answer as you keep iterating. So that's the lesson from tutorial number 1. Any questions about this before we go to alanine dipeptide from Pavel or anyone else? Okay, so let's go to alanine dipeptide. Okay, let's open it in Collab. So I don't know how many of the previous master classes have done this, but maybe Giovanni or Max know. Here we decided to do everything inside inside Collab, so you can run and generate all the data. So let's remove all of this and let's just work through it together and then see what happens. So let's start. It will take a bit of time, but it won't be too slow. Too many sessions. Oh. Okay. So is there anyone? Yeah, the collab thing is great because now you can go and try it on your system. I think it opens up a new frontier of reproducibility, right? I mean, machine learning people are already doing this. In molecular sciences, we should be doing the same. You try it, you just share the notebook and we can directly run, the developers can test it for you and see what's going on small systems, and it's super nice. So this is going to install everything. I have to type. Did anyone try alanine dipeptide? Great. At least one person tried. Bass. How do I pronounce your name?
Bas.
Bas. Hi, Bas. Did you have any adventures or misadventures when you tried alanine dipeptide?
What do you mean specifically? Oh,
I
you tried
mean,
the other stuff out of
but you were able to get it to work and get improved sampling.
The why you're
Yes.
looking for reacceptor.
Yeah. So this will take about 7 minutes. It's not too bad. Let it run. So let it run, and then maybe I should have kept it open. I think we can finish it in today's thing, but let me walk you through all of this. So when you try to do it on, the main question here is how do you transfer this from alanine dipeptide to your next system, right? So in order to do that, most of the things that you need are very simple to any GROMACS simulation in Plumed or even NAMD simulation. I mean, you can go and change all of this for NAMD or any other thing that you want. So for GROMACS, you have .gro, .mdp, .top, you need all the files, and you need an unbiased trajectory in NumPy NPY format and NumPy format. This is something you should do yourself in order to generate it. Hopefully it's not too hard to do it. So all of the methods that come out of my group, we try to keep a little bit of, we don't try to make it completely, how to say, dumbed down so anyone can use it completely blindly. We try to keep it so that you have to get your hands just a little bit dirty. We find that that is better for debugging and things like that, instead of you just using it blindly. But as the method improves, maybe this will change as more and more people use the method. So in this case, we have, it's basically Colvar, which is converted into NumPy, and we have 4 dihedral angles. You can add as many things as you want. And this is the point I was trying to make earlier, that these features that you input into SPIB should be rotational or translational symmetry invariant. Otherwise, SPIB is just going to try to pick up all those types of information. So this is a trajectory for alanine dipeptide in vacuum, which we created 20 nanosecond, 450 Kelvin, and there is a certain data resolution. Now, data resolution is how much data resolution do you need? For the input unbiased trajectory, you can get away with longer data resolution. You could get away with even half a picosecond or 1 picosecond. In the next round of SPIB, when you are taking a biased trajectory, you will have to keep finer resolution, right? Because in a biased trajectory, 1 picosecond is actually worth much longer. So that's something. So when you are doing bias simulation, it's best to print this out at your molecular dynamics integration timescale resolution, the finest you can have. That's our recommendation. This is not a .trr or a .xtc file. This is just a Colvar. So it should not be too heavy. Let's see, this is still running, that's okay. So, and then we load it, we visualize it, and we do 1 hot encoded initial state assignment. So we have number of levels and we 1 hot encoded, which is a machine learning lingo. You can go and Google and see what 1 hot encoding means. But what I want to talk about more is the parameters here. And here, Shams, who's on the call today, has showed most of the most important parameters. The first one is dt. Shams, can you, yeah, as I can see here, this is in the unit of your NumPy file, right? This is not picosecond or nanosecond. If your NumPy file that you gave it, every line is separated by 0.05 second, then this is going to be 5 multiplied by 0.05 picosecond. So if you make it 10, then this is now going to be half a picosecond, right? So it is in the unit of that one. So
yeah, that sounds right.
Yeah, we keep it what it was. RC dimension 2, for most systems, you can get it even going with 1-dimensional RC, but I don't have as much experience in metadynamics, of course, as Giovanni and Max have, but my recommendation is for most practical systems to keep this as 2. Why 2? Because if you do 3, your metadynamics is going to be too slow anyway. And if you do 1, you are probably, even with the optimized reaction coordinate, going to run into some issues. Even a 1D reaction coordinate will have some degeneracy in the value. So 2 is really the sweet spot. So for most practical systems, I recommend not bothering with this. I recommend keeping it at 2. Here comes the most interesting part, the encoder type, which is linear or nonlinear. And this is something where if you attend talks, so last week I was a machine learning workshop for molecular sciences where Andy Ferguson and others were there who are also working on similar things. And it seems a lot of people simply want to use nonlinear encoder to get the latent variable. And our group, we are starting to see now that we should be very careful in switching to this encoder becoming nonlinear in the initial stages. If you are trying to use a nonlinear encoder on top of a very good, very long trajectory coming from Anton, where everything is already sampled many, many times, then okay, go ahead with a nonlinear encoder. But for your system, you probably don't have a well-sampled trajectory, right? And so it's best to start with a linear encoder. If you use a nonlinear encoder on a crappy trajectory where maybe you have seen only one event of interest, then it's going to give you, it will be so powerful that it will just capture all the noisy features. And you will get lots of states and everything, but when you try to bias it in metadynamics, it's not guaranteed that your sampling will improve. So, and this brings up a related question as to what trajectory to input into SPIP. So for alanine dipeptide, we were able to input an unbiased trajectory where it's still running. It will finish soon. Here we were able to start with an unbiased trajectory, right? And it still worked. In the unbiased trajectory, we had one event of interest. If you took an even shorter unbiased trajectory where you did not see any event of interest, it will still work. For practical systems, we recommend, and this is the most, like, really the not the dirty laundry, but really the way to get it working. For practical systems, you will have to use a bias trajectory using some intuitive order parameter. Again, if you're doing protein ligand dissociation, it might be distance between the protein and the ligand. If you're doing crystal nucleation, it might be some existing order parameter that people have published, or coordination number or something like that. You take some input metadynamics trajectory, and that's what you feed into the method. The question then is, once you are feeding this input metadynamics trajectory, are you going to reweight it or not? So I don't think, Shams, you have highlighted the hyperparameter for the reweighting of the trajectory, have you?
No, because I'm just using unweighted.
Unweighted.
Yeah.
But that can be specified over here, right?
Yeah, of course. Using the keyword -w.
-w, the weights keyword. So I think
Yeah.
that was mentioned in the previous notebook. So in the initial state of SPIP, if you have a biased trajectory, ignore that it was biased. Just assume it is an unbiased trajectory, which sounds terrible, but that's okay. Just start with it and get started. In 1 or 2 rounds, if you get confident about the sampling improving, at that point, you should use the W parameter, the -W, which can then use the last column of the NumPy file that you input over here. And this last column, and Shams, correct me if I'm wrong, but this is where we can, in the last column, we can provide the weights, correct?
You can create a separate NumPy file with the weights and just pass that.
Okay, so there is a separate NumPy file, and the weights will be basically e to the power beta v or e to the power beta
Yeah.
v minus c, something like
Yeah,
that, right? So
exactly.
the R bias, it will be
Yeah.
coming from the R bias if we are getting very technical over here.
Yeah.
And we do that for a large number of systems. And sometimes you can just start using weights early on itself, but it might not work. Then number of neurons, 16, and this is a nonlinear encoder. So you have, Shams, again, remind me, this is for the first layer and the second layer of the encoder, correct?
So the encoder
Or this
has
is
two
encoder and
layers.
decoder.
Yeah,
Yeah.
so each encoder and decoder has 2 layers each. So for each
Yeah.
of them, you can specify the number.
So this number 1 is specifying for encoder or for the decoder?
For encoder,
And this is for decoder.
yeah, for
So
2
what
layers.
if you wanted, so the part which is, so here, where is the command which is specifying the number of layers in the encoder?
It's hard coded. So right now it's hard coded. You cannot change it. So it will always be 2 layers.
Okay.
But
And
you can
both
change the number
layers-
of neurons. Yeah.
Okay.
Yeah.
Both layers will have 16 neurons.
Yeah, exactly.
That's the idea over here. Okay, good. And the batch size, this depends on the trajectory size. So what was the heuristic that you had here, Sham? Something like 0.1% of the trajectory length?
Yeah, for us, that seemed to work really well.
Yeah, but so that you get an idea about that. So if your trajectory has 2 into 10 to the power 6 data points, you will use around 2,000 batch size, but play with it and see what goes on. Refinements is the number of times you look at whether the population is converging or not. This will, of course, take time. If you're in a rush early on, you can decrease it to smaller values. Learning rate, start with a small number, be conservative, and as your simulation progresses, you can again try to make it. So these default values are things that we have played with a lot, and we tend to preserve these values. Beta, what is beta? For beta, you really have to go into the theory, and this is something which, as the method has evolved, we tend to flip it every once in a while, and I have also forgotten. But the thing to keep in mind here is that when you're learning this information bottleneck, there are 2 things you're trying to do. It's a tug of war. You're trying to minimize how much you preserve about the input, and you're trying to maximize how much you predict about the output. And beta is this trade-off parameter. So must the number neuron 1, number neuron 2 always be the same? No, you can change it. The encoder and decoder can have a different number of neurons. Yeah, especially as you go to a linear encoder, you can do whatever.
Yeah,
So
go
ahead,
I wanted to
please.
add something. So if
Yeah.
you're running metadynamics, we recommend using smaller number of neurons in encoder and keeping more neurons in decoder because part. So that makes more sense there.
Yeah. And in general, so when you optimize this bottleneck function, you can go heavy duty with the decoder, like really heavy duty. There is mathematical reason known as variation inference, which tells you do whatever you want. Encoder, you should be careful. Encoder, if you start going too heavy duty, you will start capturing noise. So be conservative in encoder, go heavy duty in decoder. That's the general message. And okay, let's go back to this. Seed. Now, what was seed? I've forgotten. It's just a random number, right?
Yeah, it's for reproducibility.
Okay.
Random seed.
Yeah, good. Okay, looks like this finished. Let's go to next one. We'll load necessary Python libraries. And let's press this one too. And it runs. Okay, so you can see this is our trajectory. We have one transition of interest. It's not a lot. It's gone there once and come back. And we do our initial labels. When we do our initial labels, you get. So one of the very nice things we came up with is, what if you have no idea about phi or psi for some practical system? How do you come up with initial labels? So if you look up the paper, which has been mentioned somewhere in the bottom over here, this is the paper that, was this your first PhD paper, Chance?
Yeah.
Good, now the standard is high. So in this paper, Shams shows another way of assigning initial labels. Phi and psi is still some system knowledge. What if you know nothing about phi or psi? So let me open this. We call this the temporal scheme. In the temporal scheme, what you do is to basically bin the time series into discrete labels. So you say, for example, in this one here, we would have said everything from 0 to 20 picosecond is state 1. State 20 to 40 picosecond is state 2. 40 to 60 is state 3. So there is an obvious problem with this. Can anyone, including Giovanni or Max, tell me what is the obvious problem in this temporal labeling? I buy you a beer if you get it right next time we meet. Or you can type it in chat. Okay, I will tell you the obvious problem. The obvious problem is that if your trajectory length is too long, and so you want, here you can see, you don't want this initial label to become too long, right? If you're labeling everything from 0 to 100 as state 1, then it's not going to work. So you need to have a fine resolution. You need your everything from 0 to 20 state 1, 20 to 40 state 2. But now imagine that your trajectory is 1 microsecond. You are going to have 100,000 initial states, which then means that your probability state to state transition probability matrix will be 100,000 multiplied by 100,000. Your simulation will protest. It will say memory overload, go away. Okay, so that's the problem in that. But if you have a short unbiased trajectory, and so basically from, and Shams can correct me on this, but you can essentially go up to 100 initial states. Is that correct, Shams?
Yeah.
100 initial state means you have a 100 by 100 matrix. So if you know nothing about the system and all you have is, let's say, 100 nanosecond trajectory. So I would recommend, and if you have simply no idea about a physical order parameter, if you know something about a physical order parameter, then go with it, use it. As much, whatever you have, you should use it. But if you don't know absolutely anything, then you take this 100 nanosecond trajectory and bin it into 1 nanosecond state 1, 1 to 2, state 2, and things like that. So Shams, what is the best way to do temporal assignment in our codes? Have we provided material on it?
No, but I have noted it, so it will be updated in.
So we will update this tutorial. So this is a living document, right? It's not that it doesn't change. So let's do that. Okay, Shams, let's add the temporal scheme because that's going to be quite useful. Okay, great. So we already talked about hyperparameter. Any questions about this part? Anything so far? So it's mentioned here, heuristic is 0.1% of trajectory length. Okay, so now we train our model. How much time does this step take, Shams? Roughly?
A few minutes, maybe 2 minutes, not too long.
Okay, let's keep running it. And you can see it's printing out everything. And this is the question someone asked me in the first part. You can see all the states are population. So we are using like argmax to see when we visualized it. But most of them have gone down to 0 now. And it keeps running. So here, what are we doing? Here we are taking phi, psi, theta, omega, and learning a non-linear encoder as a combination of all of them. Are we using cosine and sine, or are we using directly the dihedral angle, Shams?
For this one, sine and cosine.
Yeah, but sine and cosine, and we know that, right? So essentially, we are inputting an eight-dimensional input into this, and we are learning because we have 4 dihedrals, and that's sine and cosine. So we're taking an 8-dimensional input. Our output is 1-dimensional. Which state does it lie in? And the bottleneck is 2-dimensional. That's what we are trying to learn. And you can see it's already going to 1, 2, 3 states for this much delta t. It will stop soon. After that, we will visualize it. And if you did not do sine and cosine, it still might have worked. And but where did we specify sine and cosine? In the NumPy file, it was not sine and cosine.
Yeah, the NumPy file. So I converted the dihedrals to sine and cosine in the code. So if you click on show code, it will show you.
In this one or where?
Maybe previous one.
Okay, it's somewhere. So
yeah, it's somewhere.
Have you mentioned it?
Yeah, I do.
Okay, good. Okay, great. So
because we specified number of refinements to be 15, it will keep
yeah,
going until 15. But as we can see, it seems like the result already converged from the
yeah,
state populations.
yeah.
Um,
Let it go till 15. Almost there. Okay, chat. What is the maximum system size for SPIB? The maximum system size for SPIB is billion atoms. However, it's the input order parameter space size that is limited, right? So here, what you are feeding in, we are not feeding in all atom coordinates, right? We are already feeding in some input order parameters. So what is the maximum we have tried, Shams, yet for the input space?
I think more than 1,000, almost 2,000.
1,000.
Yeah.
Yeah, 2,000. So
yeah. So it's limited by the RAM of whatever cluster you're using. It's limited by system memory, but theoretically there is no limit.
So let's say you are interested in a protein dissociation problem. So your protein 1 has 200 residues, your protein 2 has 200 residues. So the number of contacts, if you consider all pairs of residues, is going to be 200 multiplied by 200. That is a bit too much for us. So what we would recommend in this case is to consider every 4th residue or every 5th residue. If you consider every 5th residue, then you have 40 residues here and 40 residues here. 40 multiplied by 40 is 1,600 input order parameters, and that's doable. I think we have, in multiple things, gone up to 1,000. Beyond that, it starts to become slow. Again, depends on your GPU. Great question, though. Okay, so this has converged. Let's visualize it. Everything works for tellurine dipeptide, of course, there is a theorem. It's called, I won't take any names. It's a theorem. So this also works, and we get, it's loading and stuff. So the way we have, and I say we, I really mean Shams, we have modeled this collab, and Shams, you can correct me, is that if you have some other system, you should be able to use parts of this collab directly. Is that correct, Shams?
Yeah, absolutely.
What you will change is to don't run Chromax, right? You will run your Chromax on a supercomputer.
Yeah.
But this analysis part and everything, you can still do it here. If you are running out, I will get to the transferable question just in a moment. If you're running out of collab time, I recommend buying, sorry, I will not leave. I recommend buying Collab Pro. It's like 9 euros or $10 a month. And then it can run, you won't have the half-an-hour limitation. It will run much longer. And so most of this collab, you can directly use for any other system, which comes to the question of transferability. How transferable is this method learned for one system to another similar system? So Bas, are you talking about transferability of the method or transferability of the reaction coordinate?
The reaction coordinate.
That's a wonderful question. Sadly, I don't think it's going to be super transferable, but it gives you a good starting point. Okay. So we got into a discussion in one of our papers with the reviewer, because we had two systems and we were training reaction coordinate from scratch for both systems. And the reviewer did not really see sense in doing this, because if you think about traditional enhanced sampling, we bias distances, right? We bias protein ligand distance, and we blindly take it for every system and we just bias it. But in this new world, we are trying to improve the reaction coordinate. Unfortunately, so far, the reaction coordinates are not that transferable. However, they can work as a starting point. So you make a mutation in your protein, you should start with this reaction coordinate and then see whether it changes or not. It's possible that you're getting good sampling. So not to sound so negative, one answer would be start with the reaction coordinate that you learned. And if you are getting good sampling in the first round itself, great, wonderful, don't improve further. Okay. So this is how it converged. You got 3 states. One thing I want to keep in mind here is what you're showing here is the value of the deep neural network encoder in this space. And there is some merit here. Now the merit is that this boundary actually has something to do with the committer surface. This boundary is not just a random boundary. Depending on how good your input order parameters were, this boundary is telling you something about the 50% commitment surface. So that's, you're not just getting improved sampling, you're also getting the isocommitter surface from this. Yeah, any more questions? I'm really glad to see that people are finally warming up and asking questions. It's like 100% question asking rate given the small audience, which is great. Then you do your metadynamics, yeah. And I mean, this is an age-old question: what sigma to take for metadynamics? This is like any other variable. You plot at times. The heuristic I normally recommend is, well, of course, the smaller your sigma is, the more accurate your method becomes. But then the method also becomes slower. So do however you pick sigma for other variables. You plot an unbiased trajectory, look at the standard deviation, use a sigma which is smaller than that standard deviation, maybe half of that, maybe 1/10 of that. What is grid mul? Shams, I forget myself.
So it sets the grid mean and grid max of the metadynamics. It's a parameter of metadynamics. So you can use this to set how lower or how far you can set that limit to be, so that it doesn't go out of bound.
Is this a parameter coming from Plumed, or is this our parameter?
It's a Plumed parameter.
Oh, really? Plumed has
Yeah.
changed.
Yeah, if you set it too small,
Okay, good.
the metadynamics will go out of range.
Good, then I don't have to worry about it. Okay, great. And then pace is the biasing frequency, stride is the printing, and then you have grid bins. Grids are wonderful if you can use them, and this is the input file. Okay. So we create our plumed input file, and again, you can for your very important system, you can create this here, get a sense of how it is, and then go and change it on your supercomputer where you are trying to run it. So this collab, of course, you won't be doing these steps for your system here, but you should be able to replace it directly. And we run GROMACS. As we know, GROMACS runs at the speed of light. It reminds you never get a chance to kick ass. I don't know what that means. Okay, now it's running. How much time does this step take? Few seconds, I think, right?
It will take a little longer, but we can stop it and print the first few lines of the call if you'd like.
Think I can stop it?
Yeah, we can stop it. And
okay, let's write it on 2 more minutes. Okay, stopped it. Let's print out callbar. Okay, this is the beginning of the callbar. Let's see the head of the callbar, end of the callbar. Looks good. Let's convert it into NumPy array and visualize it. As you can see, in the same time, we have a bit more sampling now. It's not a lot more sampling compared to what you had earlier because it's metadynamics, right? We have not yet added that much bias. If you were to run it longer, it would have become more and more diffusive compared to what you had in the unbiased MD. And here you can, these are exercises. I mean, it's up to you whether you want to do it. These are things that I believe will help you get more intuition. But in order to use it for your system, you don't really have to do all this. The code is quite directly ready to use. And for this system where we had ligand permeation, and where this is benzoic. So in this one, we have two systems, AIB9, which is a system popularized by Gerhard Stock in explicit water, I don't know, tip 3P or something. And we consider this left-handed helix to right-handed helix transition. If you run unbiased MD in half a microsecond, nothing happens. So in this case, Shams was started from this one. In this case, getting a metadynamics variable which improves the sampling for you is actually not that easy. So he started with an unbiased system, put in all the dihedrals, and after a few rounds, he got something like this. So I really highly encourage you to go and do it yourself. If you have a supercomputer where you can run it, we have provided all the files over here, and you can directly run everything. And if anything is missing here, tell us and we will update it on the Plume Nest, and just ask us on Slack after this tutorial and we will tell you how to change it, and then you can get running. And this is a more complicated system. And this paper also has, so not just AIB9, it also has the small ligand permeation, benzoic acid through this. So here we have different types of order parameters. We have different distances, we have different angles. And this is an interesting system because when you do metadynamics, you can really speed up the energetic part of the system. There is an entropic part of the system where it has to just diffuse. That part we cannot speed up, and you will see that in the simulation. But still, it's quite nicely automated, and it improves the sampling. So I guess that's really what I wanted to say. Any more questions?
Yes, I have one follow-up question.
Please. Yeah.
So the reaction coordinate is not a transferable, but you can start from the previously learned reaction coordinate.
Yeah.
And you do that by taking the, let's say, neural network parameters that you already have and start from there. Okay. Yeah.
Yeah. So, but be careful, right, in your plumed input file, because the number of your residue might change, right, system to system. Simple things like that, you know. So.
Yeah, sure. Thanks.
So, you know, obvious things, but otherwise it's a good point to, and one of you will maybe come up with a method how to make it more transferable and things like that. We have ideas on how to come up with transferable reaction coordinates. The idea we have in mind is actually not that straightforward. It will take more time. But for now, I mean, we have reached a level, you know, where, and this is one method. There are other methods that exist out there also. Andy Ferguson has a MESA method, which does similar things. We think our theory is more sound because we are predicting into the future and we have a way of showing why it is the committer. But there are many recipes out there in this, basically this broad family of using autoencoder. And you saw Michele Parinello's group's presentation where they are doing TICA, and there are lots and lots of different methods. Now, another point I want to mention, which is a technical point, is when you are reweighting a bias trajectory, there are two types of reweighting that come into the picture. One is to reweight for the probability that we know how to do, right? Max Bonomi invented the game of reweighting in metadynamics. It's well known how to do that. There is a dynamical reweighting, which also needs to be done. That part we are being a bit sloppy about. The reason why we are being sloppy about is because we try to predict only a few picoseconds into the future. So it does not seem to make much of an effect. And we did some theoretical study on it. If you ask me on Slack, I can send you the paper where we show that it does not make much of a difference, but we are trying to improve it. So, but for many, many practical systems, what we find, like we are doing this on, let's see if I can show you, and then I will shut up. Let's see if I can open up a presentation and show you some unpublished work actually, where some unpublished work using SPIB, where we are working on like lots of different systems and getting sampling. This has nothing to do with biology, but hopefully this will give you a sense of how powerful the method can be. Let's see. Okay. Yeah, here it is. Shams, is my screen clear? The corner movies you can see?
Yeah, it's clear. I can see.
Okay, great. So this is urea nucleation in solvent. You have urea molecules. They are going to form a polymorph. Here, the input order parameters are Steinhard bond order parameters, coordination number, different types of things. And if you have done nucleation, this is a really, really hard problem to get this to happen. And here we get back and forth movement between different polymorphs. The crystal forms, it completely dissolves. And if you do nucleation, you must have seen most of the time, it's easy to actually form just a blob, something amorphous. But here you're seeing, we are forming a nice, beautiful crystal by learning the reaction coordinate on the fly. This is urea, this is paracetamol. This is unpublished work, but I'm showing it here. Paracetamol in vacuum, where you can see, again, you're learning reaction coordinate, improving it through metadynamics, learning another reaction coordinate, and it's this is glycine in water, the simplest amino acid. Here also we can form different polymorphs and go back and forth movement. These systems are so hard, and the biases tend to be so high in the system. Nucleation is like even harder than protein folding. In these type of systems, the bias easily tends to become 50 kcal, 70 kcal, 80 kcal. It's so high. So in these type of systems, we don't reweight anything. If your system has really, really deep metastable states, if every metastable state is very deep, then you can reweight. These systems are interesting because some of the metastables, the stable state is very deep, which tends to be the liquid, but the metastable states are like little blips up there. They're very, very, the barrier is very small compared to what you see for the liquid. So in these cases, if you start reweighting, you will find often that the thing blows up. So if you have a problem where you are interested in moving from one very deep state to some low-lying state and then come back, our recommendation is to just ignore the weights early on until the sampling has, that's the recommendation in general, but in problems like this, you might be better off just ignoring the weights entirely. And somehow that still seems to give good reaction coordinates for enhanced sampling. So any questions about this? This is unpublished. The glycine work, by the way, it should be out in a month or so, maybe. This one is published. We did not do it using RAVE or SPIP. We did it using my previous method, SCOOP, but it's the same idea. Now we have done it using RAVE also. Okay. So if no more questions, I guess, Giovanni, we can stop for the day.
Thanks a lot, Pratyush, and thanks to everyone for being active and asking a lot of questions.
Yeah, this was great. We had few people, but there were lots of questions, which is really satisfying to both Giovanni and to me and to Shams and to everyone. And since the YouTube video will be there, you are not just helping us, you are helping people who are watching the video. And we will keep improving the tutorial. We will add more and more examples. We will make it more and more friendly. Right now, it's alanine dipeptide. We will try to make it even easier to check it on the other systems. And if you need our help in trying it on your problem, just message us on Slack or email us. We will really, there is no better feeling than someone using your method, right, Giovanni? So we will definitely, and Giovanni sets an example for us through Plume as to how helpful we should be. So we will definitely help you if you want to use it on your system. Don't be shy, just ask us. We will help you, prepare everything and get you started. We don't want co-authorship. We are happy in the acknowledgement. Just ask us how to get started. Okay, then everyone take care. See you when I see you. Bye-bye.
Thanks a lot. Bye-bye.
Bye.